Researchers have found that Greenland's glaciers are melting faster than previously thought. A new study using satellite images finds that Greenland's glacier melt is accelerating.
For years, scientists thought Greenland's ice was changing slowly until distant seismic sensors revealed a strange pulse coming from deep within the sheet. That discovery marked the moment everything shifted, because the ice wasn't just melting, it was moving. And as that motion accelerated, it raised a question no one expected. What happens when an entire ice sheet begins to behave like a force we can no longer control? The hidden pulse of a collapsing ice sheet. For years, researchers studying Greenland believed they were watching a slow transformation, shaped mostly by temperature. Yet the first clues that something far more dynamic was unfolding emerged from instruments placed thousands of miles away. Seismologists noticed a pattern of low-frequency vibrations that did not resemble tectonic activity, and when they traced the signals back to their source, they discovered that the ice sheet itself was generating a rhythmic pulse. This realization shifted the scientific perspective, because it suggested that Greenland was not simply melting, but behaving like a system with its own internal motion. The deeper scientists looked, the clearer that motion became, especially as meltwater from the surface plunged through vertical shafts and created powerful resonances within the ice. These shafts, known as moulins, acted like towering conduits that amplified the sound of cascading water, producing vibrations strong enough to be detected across continents. The magnitude of these signals indicated that vast lakes were draining rapidly through the ice, altering pressure at the base and influencing how the entire sheet moved. As researchers connected these seismic clues to satellite observations, they realized the pulse was not an isolated phenomenon, but part of a larger pattern signaling accelerating internal change. This understanding set the stage for uncovering the mechanics that would redefine how the world interprets Greenland's stability. When ice begins to move like a geological force. As scientists followed the seismic clues deeper into Greenland's interior, they began to understand that the ice was not just vibrating, but physically reorganizing itself in ways once considered improbable. The discovery that surface lakes could vanish within hours revealed an enormous internal plumbing system, because millions of cubic meters of water were dropping through the ice sheet and reaching the bedrock with astonishing speed. When that water spread beneath the ice, it reduced friction so dramatically that glaciers began sliding forward rather than flowing gradually, and this shift introduced a new sense of urgency into glaciology. Researchers documented glaciers accelerating across distances that previously required decades, noting that some were advancing meters per hour during peak melt events. This behavior meant that Greenland's mass was no longer drifting toward the ocean, through slow deformation but moving in sudden, forceful surges. The pace was influenced not only by the volume of water, but by the discovery that much of the underlying ground was composed of soft, easily deformed sediment, which lost structural strength when saturated. Instead of anchoring the ice, the sediment acted like a weakened foundation that allowed enormous volumes of ice to slip forward with minimal resistance. The combination of meltwater lubrication and unstable ground conditions created a mechanical feedback loop that amplified movement during warm periods. Water pressure increased, ice accelerated, and friction decreased, producing conditions that allowed glaciers to behave less like frozen structures and more like mobile geological masses. This transformation forced researchers to reconsider long-standing assumptions about ice stability, setting the stage for the even more dramatic consequences recorded along Greenland's rapidly changing coastline. The era of ice quakes and violent kickbacks. As Greenland's glaciers began moving with greater speed and unpredictability, researchers monitoring seismic networks observed a new category of events that challenged traditional definitions of earthquakes. These signals did not originate from fault lines, but from the margins of major outlet glaciers, where immense towers of ice were breaking free. When these blocks calved into the ocean, they often rotated and struck the water with enough force to push the remaining glacier backward, producing what scientists termed glacial earthquakes. The backward shove, known as a kickback, transferred energy through the ice and into the bedrock, creating tremors equivalent to magnitude 5 earthquakes that were detectable across continents. Field teams along glaciers like Jakobshavn and Helheim described the calving process as both mesmerizing and deeply unsettling. because the ice did not simply detach. It twisted, collapsed, and slammed into the water with explosive power. The force of these rotations amplified the seismic signature, revealing how dynamic the interactions between ice and ocean had become. Some of the most intense events occurred during low tide, when the water level dropped enough to reduce buoyant support beneath the glacier tongue. Without that support, the ice was more likely to fracture violently, and the resulting kickbacks generated tremors that resonated far beyond Greenland. These seismic events increased dramatically over the past 3 decades, offering scientists a measurable record of how quickly the ice front was retreating. Each earthquake represented not just a moment of collapse, but a step in an accelerating process, transforming the coastline into a zone of continuous motion. The surge in glacial quakes demonstrated that the ice sheet had entered a new behavioral regime, one driven by mechanical forces capable of reshaping landscapes and altering stability on scales once thought unimaginable. This recognition led researchers to investigate the equally significant changes occurring beneath the ice, where the ground itself was beginning to respond. Greenland's bedrock begins to rebound. As glaciologists documented the increasing violence at Greenland's margins, another unexpected transformation was unfolding beneath the ice, revealed not through field measurements, but through subtle shifts in Earth's gravity. NASA's GRACE satellites detected changes so consistent and widespread that they indicated the land itself was rising as the weight of the ice diminished. This phenomenon, known as crustal rebound, had long been recognized as a slow geological process. Yet the pace observed in Greenland defied expectations because certain regions were lifting by 2 to 3 centimeters per year. Such acceleration suggested that the ice loss was not only rapid, but altering the physical shape of the continent in real time. The implications extended far beyond local terrain, since changes in land elevation affect the distribution of mass on Earth's surface, which in turn alters gravitational fields. These shifts can subtly redirect nearby ocean currents, influence the flow of meltwater along the coast, and modify how the remaining ice interacts with the underlying rock. Researchers studying these dynamics noted that rapid uplift could eventually destabilize grounded ice by lifting sections unevenly, creating fractures that encourage further movement toward the sea. This rising bedrock also provided a new perspective on how interconnected Greenland's processes had become. The ice sheet's collapse triggered seismic events that signaled instability, and that instability reduced pressure on the land, allowing the crust to rebound faster. Each component reinforced the others, forming a network of changes that challenged earlier models predicting slow, predictable behavior. Understanding this rebound underscored that Greenland was no longer responding gradually to climate forces, but participating in a fast-moving transformation, with global consequences still coming into focus. The threshold problem. As scientists integrated seismic activity, accelerated glacial flow, and rapid crustal uplift into a unified picture, they realized that the changes occurring across Greenland were pushing the ice sheet toward a threshold long theorized but never observed at this scale. This threshold, known as the melt elevation feedback, describes a process in which shrinking ice lowers the surface height and exposes it to warmer air, accelerating melt in a self-reinforcing loop. Researchers initially believed this feedback would activate gradually, yet the pace of recent ice loss demonstrated that the system was responding more quickly than anticipated because the ice sheet was already sinking into temperature zones capable of sustaining continuous surface melt. Studies conducted after 2024 showed that the global temperature increase required to initiate irreversible decline was likely lower than earlier models suggested. While climate agreements targeted a limit of 2 degrees Celsius, new evidence indicated that instability could begin around 1.5 degrees, a threshold the planet had effectively reached. This meant that even temporary reductions in temperature would not halt the feedback once it became self-sustaining, because the lower ice surface would remain exposed to conditions that promote melt. This realization altered the scientific conversation from one focused on slowing change to one centered on managing consequences, since the momentum built into the system suggested long-term transformation, regardless of short-term climate variability. When combined with the mechanical forces accelerating the ice toward the ocean, the feedback loop represented a critical shift in how researchers understood the trajectory of the Greenland ice sheet. the recognition that a tipping point may already have been crossed led directly to an examination of the global systems that would be affected as the process continued. The global domino. As evidence mounted that the Greenland ice sheet was approaching a self-sustaining decline, researchers turned their attention to the coastal shelves that acted as its final stabilizing barrier. These floating platforms function like a structural cork, slowing the discharge of land-based ice into the ocean. Yet satellite records showed that more than a third of their volume had disappeared over recent decades. With each loss, the natural braking system weakened, allowing ice streams to accelerate toward the sea and increasing the rate at which global coastlines would feel the impact. The immediate consequence was a measurable rise in sea levels, but long-term projections revealed a more complex chain reaction. The addition of vast amounts of cold, fresh water into the North Atlantic threatened to disrupt the Atlantic meridional overturning circulation, the system responsible for regulating temperatures across much of the northern hemisphere. Scientists warned that even partial weakening of this circulation could reshape weather patterns, bringing harsher winters to parts of Europe, while shifting rainfall belts across the tropics. Cities built around predictable coastlines faced growing uncertainty because the retreat of the shelves meant that future sea level rise would unfold with fewer natural buffers. Regions from New York to London and Tokyo were included in risk assessments that highlighted the vulnerability of densely populated coastal zones. These implications demonstrated that changes in Greenland were not isolated events but components of a larger planetary response, setting the stage for understanding how rapidly the Earth system was entering a new operational state. Greenland's shifting ice, rising land, and widening scars reveal a planet responding to pressure with unmistakable force, leaving humanity to face changes already set in motion. To explore these stories as they unfold, stay connected, subscribe for deeper investigations, and join the journey to understand our transforming world.